All right. Day 2 of vectors, resolution into components. All right, so we learned yesterday that a vector can be represented as the horizontal component x times vector I plus y times vector j. And y is that vertical component, where you can get the x component by taking the magnitude of the velocity vector times cosine of the direction angle, and y is the magnitude of the velocity vector times sine of the direction angle. So this question says, if A has a magnitude of 5 and a direction of 70 degrees, and B has a magnitude of 6 and a direction of 25 degrees, find the resultant as the sum of two components. So the first thing we're going to do is turn vector A into its component form, into xi plus yj. And so what we know is vector A has a magnitude of 5 and the direction angle is 70 degrees. And so the x component would just be 5 times cosine of 70 degrees, and the y component will be 5 times sine of 70 degrees. Yeah. And so I'm going to leave them in this form because once you put them in your calculator, it's going to round it. And I don't want rounded answers yet. I want to wait until the very end before my rounded answers, before I start rounding. So that means that vector A is 5 times cosine of 70 degrees times vector I plus 5 times sine of 70 degrees times vector j. Let's do the same thing for vector B. Vector B, its magnitude is 6 and the direction angle is 25 degrees. So the x component of vector B will be 6 times cosine of 25 degrees, and the y component will be 6 times sine of 25 degrees. And we put those together, and again, I'm going to leave them exact for right now. So that way I'm not rounding until the very last step. We will end up rounding, but the more you round in the middle, this is a J, it's a weird funky J. The more you round in the middle, then the more off your answers will be. All right, so now we want the sum of these two vectors. So when I go A plus B, that means I'm going to be taking this guy plus this guy, right? So I've got the 5 times cosine of 70 degrees times vector I plus 5 times sine of 70 degrees times vector j. That's A. And then I'm going to add to it vector B. And then what you'll do, I'm going to run out of room. Just barely squeezed it. Okay. Then what you're going to do is you're going to add the i's together. You'll combine like terms, right? So that means that in front of I, you'll have a 5 cosine of 70 degrees plus 6 cosine of 25 degrees times vector I. I'm combining like terms, right? And then I'm going to add to that, for the j, I've got 5 sine of 70 degrees plus 6 times sine of 25 degrees times vector j. Now I'll put these in my calculator. Keep in mind, we are going to end up using it on the next part for magnitude and direction, so I am going to store them. So then that way, again, I'm not rounding until the very end. All right, so let's put this in. Okay. So the first thing I'm going to put in is 5 times cosine of 70 and the parenthesis for the cosine of 70, and then plus 6 times cosine of 25. Enter, and I get that this is, I'm going to go to 3 decimal places, so a 7.148 times vector I. Now before I go and figure out the y component of adding these together, I'm going to store this. I'm going to store it under A. I'm going to write myself a note that I stored it. I stored this guy as A. All right. And then I'll do the same thing with the second one. 5 times sine of 70 in the parenthesis plus 6 times sine of 25. And it would help if I hit the right numbers. 25, there we go. 7.234. I'm going to go to 3 decimal places. So this would be a plus 7.234 times vector j. But before I clear this out, I'm going to store this guy. I'm going to store it under B. So stow, arrow to the right to underline B. Notice I haven't stored anything under B yet, so that's why it's blank. Hit enter, and there you go. Now it's under B for, my answer. All right, so answer for part A is just that guy. But we're going to use these values to find the magnitude and the direction. Okay, so now finding the magnitude. Magnitude is just the length of this. And you use, for the magnitude, you're just going to use Pythagorean theorem. All right, so magnitude of A plus B is going to be the square root of the first guy squared, which is my stored A value squared, plus my stored B value squared. And you'll see that, these guys, obviously we approximated them, right? This guy was about 7.148, and this guy was about 7.234. But if we round here and we use these guys, our answer is going to be off. So I'm going to use the stored values. I've got square root of my stored A value. You're going to bring up memvar, enter squared, plus memvar, arrow to the right for B, hit enter, and then square that. Yes, and so I get that it is about 10.1698. Blah, blah, blah. If I go to 3 decimal places, my answer will be 10.170 for the magnitude if I'm going to 3 decimal places. All right. They also want us to find the direction angle. And how you find the direction angle is, this obviously is not one of the ones you've memorized, right? So you're going to use tangent. You're going to use the fact that tangent of theta is equal to y over x. Well, but the y is that stored B value, and the x was the stored A value. And so I'm going to go, and to find theta, you're going to take the inverse tangent of both sides. So of my stored A over stored B. And that's what you'll put in your calculator. Inverse tangent of B divided by A. Inverse tangent of B over A, and it gives me about 45.343, so 34 degrees. And I don't know why we only go to 2 decimal places for the angle, but that's what we do. Okay. All right. There's that problem. Hopefully that was pretty straightforward. The next one you're not going to like so much, but yeah. All right, example 2 says, a ship sails for 20 miles on a bearing of 325 degrees and then turns and sails on a bearing of 250 degrees for 7 more miles. Find its displacement vector as a distance and a bearing. All right, so I'm going to draw a north, south, east, west. You're going to be up. You're going to go around 325, so you're going to be up here in quadrant 2, and then you're going to, from there, so I kind of need more room up in this corner, if that makes sense. So I'm going to draw my north, south, east, west kind of low down here. North. Okay. All right, so first of all, it sails for 20 miles on a bearing of, remember, bearing means from the north going clockwise. So 325 degrees, you're going to start here. You would go, this would be 90, 180. 270 and then 325, so to about there. You're starting here and you're going to draw. This one has a length of 20. This one has a length of 70. You want to kind of try to be proportional to make it look right. So let's say I go to like there. Pretend like that's a straight line. I really should have pulled out my ruler. But this has a length of 20. All right. Now, this is a vector like that. It's got a 20, and this was 325 degrees. Then it changes directions. So when it changes directions, what you've got to do is draw a new north, south, east, west direction, because now this is your new starting point. And this time it has a bearing of 250 degrees. So from this point, starting from the north, you would go 90, 180. If you went all the way to here to this negative x-axis to the west part, it would be 270, but we only want 250. So I'm going to stop short. And if this length is 20, that would be 10. So I want to try to kind of be proportional. I think about that would be 7. And this was 250 degrees. All right, so this is its new position now, right there. That's the new spot. They traveled this way, and then they changed directions and went this way, and then now there's a new spot. All right, so find its displacement vector, which that is this guy, the resultant vector, from the beginning until the end. That, I'll call it R. Now, as we're going to find the distance of it, and we're going to find the bearing. So we're going to find what the direction was there. Okay, so let's find the distance first. So the distance here, well, in order for me to find the distance, I'm going to redraw the triangle for a minute, just so you can see. I know I'm making that look like a 90-degree angle, but I don't mean to. Not intentional at all. I just suck as a drawer. Okay, so here's your R. I know this is 20. I know this is 7. So I would have a sassy triangle, right? Side, angle, side, if I knew this angle here. I know I made it look like 90, but it's not. Okay, so how are we going to find it? Well, you're going to use this fact here. We know that this is 250 degrees, right? And I know that if you subtract, here's 250, right? And then if you subtract the fact that, well, no, we need to use something else too. We need to use the fact that I need to be able to figure out what, let me do a different color, this one. I can figure out what this angle is because I know what this angle is. If that makes sense. I know they kind of look weird, but here's what I know. I know I have two parallel lines, this east-west line and this east-west line, right? And it's cut by the same transversal. And so what I know is if I can find this angle, I can find that one. And that's where these two are coming in. They're coming from this transversal right there. Right, two parallel lines cut by that transversal. Well, this guy's actually pretty easy to find because this angle right here, this one, it was 325. But if you subtract 270 from it, it'll give you from here to there. Because from here to there was 270. So minus 270, which gives you 55 degrees. So this angle here is 55 degrees, which also means that this angle right here is also 55 degrees. Yeah. And so if this guy is 55 degrees and I want this angle in between here. Well, I know that's 55, and I also know this guy is 90. So to find this angle here, this pink one, I would do 250 minus the 90-degree angle, which was from the north to the east, right? And then minus the 55, which will leave you with 105 degrees. That's how I got that. So this little pink angle there, the pink angle there is from all the way to the edge there is 250, but I know this guy is 90, so I subtracted the 90 and I subtracted the 55 there, and that's what gave me that was 105 on the inside there. Okay, so now it's a sassy triangle, right? Side, angle, side, and I can use a lot of cosines to find the distance of this resultant vector. So it's r squared is equal to 7 squared plus 20 squared minus 2 times 7 times 20 times the cosine of the angle in between, which means that your r will be the square root of that whole thing. Yeah. And so I'll put it in my calculator. We're going to go square root of 7 squared plus 20 squared minus 2 times 7 times 20 times the cosine of 105. And I get that r is about 22.8357, blah, blah, blah. I'm going to round it, but I'm also going to store this because I'm going to need it for the bearing. And so that will end up giving me my answer. If I go to, does it tell me? Let's go to 10th spot. 22.84 miles is the distance of the displacement from where he started until where he ended. 22.84 miles. Okay. Now, bearing. The bearing of this guy is going to be, let's see, what other color do I have? We'll do it in green. The bearing of the resultant vector would be from the north, going clockwise, but stopping right there. Yeah, that's going to be your bearing. And so what I need to do is I need to figure out, I know it's 325 until the inside. So do you see that if I find this angle right there in purple, if I find that angle there, then I can do 325 minus that angle, and that'll give me the green bearing. Yeah. So we're going to do this in 2 steps. First of all, to find the bearing, I'm first going to find the purple angle, right? And so I'll call that theta. Sine of theta is, and that's this angle right there. Yeah. Okay, that's this purple matches that purple there. So it's sine of, I'll call it theta, over 7 is equal to sine of 105 degrees over the magnitude of that resultant vector, which I have there, and I forgot to store it, so I'm going to store it under A right now, so that I'm going to take it as my, divide it by my stored A value. All right, well then that means your theta will end up being, you need to multiply by 7, and then take the inverse sine of that. So here we go. Inverse sine of 7 times sine of 105, and the parenthesis divided by my stored A value. And that gives me about 17.223. So about 17.22 degrees. Now that was just the purple angle, right? That was the purple angle. And so the actual bearing is going to be 325 was all the way including the purple angle. 325, not 325. 325. Oh, this pen is just smearing like crazy. Ugh. and then subtract from it that purple angle. And that's going to give you 307.78 degrees is the bearing of that resultant vector. All right. Maybe this is going to cooperate with me. It's playing hide and go seek with me. There we go. Okay. All right. I hope you guys are having a fantabulous day. Bye.